right. Welcome back. So let's move on directly to XML schema. Again, what I want you to see is that XML schema, JSON, it doesn't matter, it's all the same. They all allow you to constrain the structure of the trees that we are looking at as JSON and XML. And this is in particular useful, again, I repeat, if you have millions or billions of JSON objects, or if you have millions or billions of XML documents, you can make sure that they match the schema. And this is very important for data sets. If you download a data set, typically there will be a schema. In fact, it's very common that on the dataset web page, they also give you the schema. Very often they do that. Of course, if you don't use the same schema technology, you will need to convert, but this is fine. All right. So before I show you XML schema, you should know there's others. There's another one called Schematron. There's another one called Relaxing or RelaxNG. I'm not exactly sure how you pronounce it, but there are several of them. XML schema is kind of the official one that was also standardized by W3C, which is the same people who standardize XML. But you should just know there's others, but they all do the same kind of things. You wouldn't believe the number of hours I try to spend getting rid of that pop-up. I'll have to wait for the next macOS update probably to see it disappear. Anyway, so XML schema. Same idea. The instance is on the top, the schema is at the bottom, and I'm showing you cases where the instance is valid against the schema at the bottom. The first thing you notice here is that a schema is also XML syntax. Just like for JSON, the schema was also in JSON syntax. It doesn't have to be, right? It's just very common to do it that way because it's very intuitive. So what do I want to achieve here? I want to achieve that I have an instance, which is an XML document, and I want to specify that my top level element is foo, and that inside my element foo, I want a string, text. Well, technically, if you look at XML, there's only text. There's nothing else than text. It's not like in JSON where there's string, number, Boolean, null. Here, you just have text. So whatever happens, you're going to have to look at the text as some lexical representation of whatever type you want to parse, right? But in that case, I just want a string. So that can be any text. Technically, I don't really care what this is. This is text. It's just what I came up with when I prepared that slide. And so what I'm saying here is that I have a schema that has an element, the name of which is foo, and that has the type string. Do not be scared because you might have noticed the namespace here. Who noticed the namespace? I showed you namespaces 2 or 3 weeks ago, right? So don't be scared. Schemas live in a namespace. And you recognize the namespace here has www.w3.org. That's the W3C domain. If you go there, there's a fancy website with all the standards. And so they have this 2001, because that's when it was designed, XML schema. That's the namespace of the schema. It's always that one. And it's associated typically with prefix XS. You might find people who use XSD instead, XML schema definition. It doesn't really matter because I told you prefixes are irrelevant. You might see that the types are also in that namespace. Something that you might not have seen before, but you see type XS string. That's fine. It's fine to do it that way. You're basically saying that it's a built-in type in the XML schema namespace that's called string. The types, however, even though they have this extra XS colon in front of them, this is exactly the same list of atomic types as in JSON, the list I already showed you. It's exactly the same one. The only difference is you need to remember to put the prefix in front. That's all. It's exactly the same list. That makes it easy, right? That was on purpose, actually, when we defined JSON, we used exactly the same type list. All right, so foo is a string, and yes, it is a string. This is text. So the document is valid against the schema. Next, let me use an integer. So now you see the difference between the two is that now you have type XS integer. So now that's requiring that I should be able to parse whatever text there is between my tags must be parsable as an integer. Is that the case? Well, these are only decimal digits, right? 142,857. That's the lexical representation of an integer. So yes, this is valid. And what I do is that once I have validated it, in memory, I'm no longer going to have 142857. It's over. In memory, I'm going to have a more efficient representation, maybe on 32 bits of that integer. Do you understand that? I will no longer have the decimal representation in memory. I'm directly going to have maybe in base 2, because then it's much quicker to add and compare and multiply. All right, so this is why it's useful to have types. Okay, so these are atomic types, right? So now I can specify elements that have an atomic type. What does it mean? It means that the element has no further elements nested in it, only text. But of course, there are also XML documents that might have elements in elements in elements, right? Just like you have arrays in objects in arrays in objects. So here I have elements in an element. Last and first are nested within person. That's obviously not atomic, right? Because now I have nested structure. So how do I do this? Do not be scared. It's very verbose, but verbose does not mean complicated. It just means that it's verbose. It uses more space. So here we have an element named person. That's exactly the same as excess element named foo. So here excess element named person. But now I don't have this type blah, blah, blah. Instead, inside this element schema tag, I have complex type sequence. And now I'm listing my elements. So we have a first element called last that is a string, second element called first that is a string. Is that the case? Well, Einstein is obviously a string in last, and Albert is also obviously a string in first, because there's no nested elements. So this is fine, it's valid. Who agrees? All right. Don't be scared again by the verbosity. It's always complex type sequence when you want to do that. And yeah, all right. The paradox is, maybe you will not take my word for it, but paradoxically, verbose is simpler. It's scary at first, but actually it's simpler, because when it's verbose, there is less ambiguity or room for misinterpretation because you have a very specific pattern. Okay. Now there is some other thing that I can do that I didn't have in JSON, because in JSON, the keys must be unique within an object. I cannot repeat keys. Well, I should not repeat keys, but I told you to treat the should as a must, right? But in XML, it's totally fine to have repeating elements, totally allowed. But in the schema, what I can do is specify exactly how many times I'm allowing for the elements to repeat. I can specify that. So for example, for 2 to 4, of course, I called it obviously that way because I want it to appear between 2 and 4 times. But how do I do that? It's min occurs 2, that's the minimum number of times, inclusive. And max occurs, also inclusive, is the maximum number of times. So it can be twice, thrice, 3 times, or 4 times. Okay. What about 0 or 1? Well, min occurs 0, max occurs 1. It basically means it's optional. Can be there, cannot be there, but it cannot repeat. Okay. And then the types 2 to 4 must be a string, foo bar, foo bar, foo bar. Well, I was a bit lazy when I did that one. I just copy paste it. And then you have 0 to 1 is a Boolean. Yes, that's true. That's a Boolean. Okay. Who understands that the document is valid against the schema? Awesome. Perfect. By the way, here I only put the complex type part, right? I just wanted to focus on that, but obviously the complex type must be inside an element and a schema, just the same, right? Schema must always have the schema elements. Okay. All right. That's just a slide I moved around and I forgot to delete it, the dates one. All right. What can I do also? I can specify that an element must be empty. I can do that. It's very easy. I just do this complex type sequence, the same thing as I had here, except that sequence has nothing in there. I just directly close it. That's the way you have the slash on the right means that it's empty. And that's pretty much it. If I say it's a complex type that is a sequence of nothing, that basically means it's empty, right? I don't think I have much more to say about that. That's how you restrict an element to be empty. And that's, again, the power of XML. That is something you cannot do in JSON. In XML, you can have texts and elements that are mixed together. So in that case, we have some text and some bold text that looks a lot like some publishing industry use case, right? With some bold B for bold, right, in XHTML. This is called mixed content. It's neither quite like this, that would be highly structured, that's typical for data sets, but it's also not like this, that it's purely atomic. It's a mix of both. You both have some text and some that would technically be atomic, but you also have this B bolt that is a nested element. So this is mixed. And the magic word to allow for mixed is basically mixed true. You see, right here. I just defined the same complex type sequence, but I had mixed true. This is how I allow for some extra text to appear there. If there wasn't mixed true, I would not be allowed to have text here and here. I would only be allowed to have B nested. Who understands this mixed? All right. And remember, why on earth do we want mixed? This is all for the publishing industry. This is for people who use XML to store books, scientific papers, and so on and so on. So it's publishers. And the typical use case for mixed is that you want to format text, or you want to have sections, paragraphs, chapters, and so on and so on. So this is the use case. All right. This is one of the very few things you cannot do in JSON. For this is where you should really be using XML if you want this publishing use case. Okay. I can also validate attributes, by the way, not just elements. So how do I do that? Well, let's take a complex type again with Einstein Albert with last and first. So complex type sequence, you already know, right? Last and first are strings. But now below the sequence, I can also add one or more attributes schema declarations. And here I'm saying I have an attribute, the name of which is birth. The type is date. It's again from that big menu I showed you. Date is one of the many types that you have in there. And you see, it is a date indeed, 1879-03-14, right? The ISO 8601 standard. Okay, that's it. Who agrees this is valid? Document is valid against the schema. Okay. Again, do not be scared by the verbosity. What I hope is that you saw that JSOund is really super simple. That's the one that you should really focus on for learning, but you should know that there are other schemas for XML and so on. They look verbose, but if you do the exercises, you'll see it's always the same. It's really the same pattern. That's an example. You remember the great language game I showed you in JSON earlier with an example with JSOund. We can also convert it to XML. This is another instance of my great language game. There's 16 million of them in the data set. I don't know if I already explained the structure, so I think I did. Here, it means that somebody played that game. They were listening to some audio that was Norwegian. They were given the choice between, is that Maoric, Mandarin, Norwegian, or Tongan, and they correctly answered Norwegian, right? And whoever did this was from probably Australia, okay? And they did this on August 19th, 2013. That's one play. And you have 16 millions of that in the data set. You can download it. It's on the website, and probably on the exercises, we also point to that. Note that the data set is in JSON. Here, I just manually converted it to XML, which you can do. But why did I do that? I wanted to show you the corresponding schema as an example. And you see, this is all familiar here. You see complex type sequence, element, complex type sequence. The only thing is that we have multiple levels of nesting, right? But it's always the same pattern. Who has an intuition that this matches? The document on the left is valid against that on the right? Okay. Do the exercises. Make sure to solve the exercises and to make sure you understand that. Download Oxygen. If you haven't already done so, you can get it for free from the ETH IT shop. We have a license for you. Download it. And in Oxygen, you can put an element, put a document, put a schema, and click on a button, and you get a green or a red flag that tells you it's valid, it's not valid. If it's invalid, it even gives you the error messages, exactly what you need to fix. All right, so really use Oxygen for the exercises. Do not hesitate. Don't do everything on paper. Use Oxygen. It makes your life easier. And this is just the geeky part in me. That's obviously XML schema is XML. So what about validating XML schema against itself, right? An XML schema is an XML document. It follows a structure. So there is a schema of schemas. This document here is valid against itself. And if you look at it, it actually is the entire document is in the internet. If you look at it more in details, you will maybe convince yourself of that. It's only a curiosity. I'm not saying it's useful or anything, but you know, I enjoy that kind of things. Okay, that's it. with XML schema. Again, what do I want you to understand with this? XML schema is really doing the same thing as JSON schema. It's just doing it on XML rather than JSON. For whom is that clear? Okay. And again, solve the exercises to make sure that you get more familiar with that. That was only an overview. Okay, now I'm gonna switch to a hype. I don't know if it's still a hype today, probably is a little bit on social media. Who ever heard of data frames? Who heard about pandas? A lot of people heard about pandas. Pandas is about data frames. So it's a buzzword that grew in popularity because a lot of people like to write tweets and to write a lot about that on social media. So I'm going to give you a perspective on data frames that might not be the perspective that you've seen at other places or that you saw explained by the people who write this. But I have good news, is that that perspective is super simple to explain, given what I have shown you before. A data frame is just valid JSON. That's all it is. And I'm going to show you that with visuals, with concrete drawings, because when you have validated JSON, you can actually draw fancy tabular-like diagrams, which is actually quite cool. And a data frame is just that, once you have understood that. Okay, let's start simple. I'm going to start with some schema for a flat structure. I just have a bunch of keys with atomic values, nothing nested, right? So it's just ID is an integer, name is a string, living is a Boolean. That's JSON, right? It's not an actual document, it's just the schema, right? The actual document is going to have, for example, ID 1, name Einstein, living false, right? Imagine I have 4 JSON documents, 4 of them that match that schema. Do you see that I can, instead of looking at these 4 documents as JSON, I can instead represent them with the table on the right? Who sees that? Who agrees with that? Who doesn't see it yet? I think you all do. Okay, so the first document has ID1, name Einstein, living false. The second one has ID2, name Mirzakhani, living false. The third one has ID3, name Turing, living false, and so on, right? Okay, so these are 4 JSON documents. But do you see what happened here? The JSON documents, it was just text, right? So I showed you, that's fine. We can parse the text as trees because it's JSON. So I can draw a JSON tree. But these trees here that you would draw out of documents valid against that schema, they would be particular. They would be very flat, these trees. They would just have the root and then ID, name, living, and with a value, and that's it. These are flat trees. Because of that schema, instead of looking at them as trees, 4 trees, instead of them, I can represent them as this table right there. Now you're going to tell me, why are we even using JSON here? And instead, indeed, you would be right. We shouldn't be using JSON for that. We should be using a relational database, right? For this, SQL and a relational database is probably a better choice. But what I want to show you here is a generalization of that, more powerful than relational databases. And this is what data frames are actually about. Okay, but this is actually still a data frame. A relational table is always a specific kind of data frame. That's the case where it's flat and regular structure. Now, let's try to generalize. This is no longer a relational table. Why? It breaks the first normal form, right? You see these lines here, it's no longer a regular table. I have these horizontal lines that divide my cell here. You see, Albert Einstein, it's divided like that. Alan Turing, this is no longer a relational table, but it's a data frame. So how did that happen? How did we get these strange horizontal lines that are only going through one column? Well, it's because of this name that is an array of strings. Now we have nestedness. We are nesting an array inside the object. And we can still draw it with vertical and horizontal lines. Because of this schema, we know it's always an array of strings. So we can just represent these strings in each array as a vertical list like this. So this is why we can draw the data frame as is shown on the right, right? So for example, the first JSON document would have ID1, name is an array with the string Albert and the string Einstein, and living is false. The second one, ID is 2, name is an array with 1 string, Mirzakhani, and then living is false, and so on. And we have 4 JSON objects like that. Who agrees that the schema corresponds to that visual? Right, okay. And again, we can do that because we have the schema. If I don't have a schema, I can't do that because I have no guarantee that my documents will fit that pattern. But if I have a schema, I know about it. Okay. Next, let's, instead of nesting an array, we nest objects. So now in name, we nest an object with first that is a string and last that is a string. Now, this is the data frame that I'm going to get. Maybe there's too much sun shining on the, and of course, it's always nice to have the visit of the sun, but not if it prevents us from looking at the slides. It comes from over there. Try this. Hopefully that's going to help. All right. So what's going on here? Well, it still looks at the table, but look at the headers of the table. Now I have name and I have subheaders first and last that are in there. So it's a substructure of name, right? So my first JSON document has ID 1. Name is an object that has the key first with Albert and last with Einstein, and then living is a Boolean. Who understands the correspondence? Okay. That should be intuitive, right? Okay, so we nested an object now, and again, it's because of this schema that we can do that. Now, let's have both arrays and objects. So now I have a schema that says that I have an array of objects, but not an array of any objects, an array of objects that all look the same, an array of objects that all have a key name that is a string and type that is a string. So now this is how I can draw it. This is even more generic than before. My first object has ID 1, who is an array that has two objects. The first object is name Albert type first. The second object in my array is name Einstein type last. And then I have living that is a Boolean false, and so on and so on. In the second object, there's an array of only one object. In the third object, there's an array of two objects. In the fourth object, there's an array of one object. Who agrees that the visual representation is like the schema? Who doesn't see it? Okay. So this is the most complicated one. So if you understand this, then you understand data frames. That's pretty much it. Of course, in reality, you can have more columns and so on. You can have more nestedness, but this is pretty much the idea. So as you might imagine, this doesn't work for all schemas, right? It works for schemas that look like this sort of structures, then you can draw data frames. But a data frame is basically a collection of JSON documents that has been successfully validated against schemas that look like this, right? This. And again, that's a specific use case is the relational database, but if you have this, again, you shouldn't even be using JSON, you should be using PostgreSQL or whatever, but it's generalized to nested structures like this that you will not find normally in a relational database. Okay. This is a data frame. Okay, we'll see them again. We'll see them when we study Spark. We'll actually manipulate data frame. If you use pandas now, you have a different perspective. When you will maybe no longer look at your pandas data frames the same now, but that's pretty much it. Okay. Okay. And as my last words for after data frames, what I want to basically, let me start with the most important message, then I'll talk about the format. What I want to say is, imagine now that you have a collection like that, but with a billion objects, a billion objects like that. So that would be a billion rows in this data frame. And that data set is stored in JSON. You can download it over the internet, right? Now, the question is, how large would that JSON data set in the JSON format? Probably very large. It has a lot of redundancy. For example, ID, who, name, type, living, it's repeated a billion times because in JSON, you need to repeat the keys every time. Is that efficient? No. Why is that not efficient? Because we have a schema here. We know it's always going to be ID, who, name, type, living. We know that. Is there not a way that we could save some space by not saving every time the keys ID, who, name, type, living? Well, the answer to that is obviously just like that's what CSV is doing. In CSV, we don't repeat the headers, right? In CSV, we just put the header on the first line, and then we don't repeat it. We just put the values. Can we generalize that to JSON and to this? The answer is yes. And the secret is, I'm going to give you my favorite format for that. It's called Parquet. It's a data format that you can convert your JSON data sets to if you can validate them against a schema like that. Parquet is just a way to store a data frame like what you see on the right, using much less space than you would in JSON. So if you ever have a semester project or a master's thesis or whatever later, or in your PhD thesis, if you're a PhD student, and you download a data set that is all in JSON, and it's 5 gigabytes, takes a lot of space, and you need to query it and query it and query it all over, if it so happens that the structure of your data set can be drawn like this as a data frame, then the first thing you should do, that should be an automatic thought, is convert it to Parquet. Instead of the 5 gigabytes, maybe you're only going to have 500 megabytes, 10 times less. Why is that important? Because you have less bytes to read from disk. It's going to take 1 hour instead of 10 hours, right, to process. Well, for 5 megabytes, maybe not 10 hours, but let's say 1 minute instead of 10 minutes. Right? And a factor of 10, if you're working on your thesis, if you run the queries 100 times, fixing things every time, you're going to appreciate the performance gain, that it's 10 times faster. So this is why the concrete lesson here is you should think of converting a valid JSON collection to a format like Parquet, that is a binary format. Okay. So now let me talk about formats, now that I have said that. So for an abstract perspective, what is a data set? It's a list of maps. It's a collection of JSON documents, but JSON document is often an object, and an object is a map. Now the collection can be seen as a list as well. Technically, it's not an array, it's a collection, but still a list. Now, a flat data set might look like the data frame you see on the left, that's the relational table. A nested data set might look like what you see on the right, right? Now we saw that we can also draw it as a data frame, but here I didn't bother, I just put the nested tables. But you could also put name and living as subheaders like we did before. What I want to show you here is the contrast between flat and nested. You can have flat data sets, first normal form, nested data sets. JSON can do that. JSON can cover the flat data sets like this, all values are atomic, and JSON can cover the nested data sets like shown on the right. For the left, CSV can do it as well. For the right, CSV cannot do it. Okay. Now we have a second dimension. So the first dimension is flat nested. The second dimension is homogeneous, heterogeneous. Heterogeneous means you might have missing columns or you might have extra columns. This is how it looks like in JSON. Homogeneous, CSV can do it. Heterogeneous, well, CSV can kind of do it if you leave values unspecified, right? But it would be not very natural, but you can. So heterogeneous means that, but you cannot have extra values with CSV. You can only omit values. Okay. Now let's have very scary, the two of them. So on the left is the beautiful world of relational databases. It's flat, it's homogeneous, it's a relational table. On the right, you have nested heterogeneous data. In fact, there is no schema there. And the way I drew it was completely arbitrary. In fact, it would be very hard to draw in a generic fashion. It's easy to draw only if you can turn it into a data frame. Your schema is simple enough. Okay. And nevertheless, in spite of this complexity, you can do it in JSON and XML, right? So on the left, you have a flat homogeneous data set. On the right, you have a nested heterogeneous data set. So what I want to show you is JSON is a generalization of CSV. XML is also that, right? And I insist XML also in exactly the same way. Might be more verbose, but it achieves exactly the same thing. It doesn't matter if you use JSON or XML for this. Okay. So now you have plenty of ways you can store that data. XML and JSON are the two we covered that have trees. CSV works if your data is flat and homogeneous. Data frames I've covered as well. And once you have a data frame, you can store it as Parquet, as Avro, that are other formats. LibSVM is also the same, but for machine learning applications. YAML I covered, that's also a text syntax. Protocol buffers, that's by Google. It needs a schema. You can only need protocol buffers if you have a schema, but it's binary. But technically, protocol buffers is like Parquet and Avro. It's similar. Okay. So how do we sort the mess here because I threw all of these data format names to you. How do we sort this out? Well, you can look at this along different dimensions. One, nested versus flat. XML, YAML, JSON, Avro, Parquet, data frames, protocol buffers, they support nested. CSV doesn't support nested. Next, you can look at text versus binary. JSON, YAML, XML, CSV, this is all text. libsvm, Avro, Parquet, protocol buffers, this is all binary, meaning you cannot read it as a human, just zeros and ones. Data frames, it's a logical concept. It's not an actual format. Okay, and schema required or optional. Well, JSON, XML, and YAML don't require a schema. You can just store the data without a schema. However, Avro, Parquet, CSV, and protocol buffers need a schema. So this is how you can classify these technologies, all right? Now, optional part, I just want you to feel good now with this slide I'm going to show you. I wanted to show you a bit of Parquet, the type system of Parquet. Remember that in the previous hour, I told you about the type systems in a generic way. So the slide that I'm about to show you now should make you feel good because it should give you a déjà vu impression. Right? You've already seen that. This is the list of some of the available atomic types in Parquet. Does it feel familiar? It should. We've already seen that. An integer on 32 bits, an integer on 64 bits, double, decimals, strings, binaries. Of course, the names are not the same, but it's like you go to the Auschwitz and hear Auschwitz instead of Zurich, right? It's just another way of naming things, but that should feel familiar. So if you want to learn Parquet, all you need to do is look at the documentation, look at the types, and see how they map to the other type systems. There will be extra types. There will be some that just have a different names. Some are missing and so on. Structured types, list, maps, familiar territory. It's just that they are called list in uppercase and map in uppercase. But that's the same as arrays and objects. Okay. Protocol buffers also, so you feel good. This is a schema in protocol buffers. And again, I'm saying I have a string that is the last name, a string that is the first name, title, that's a nested type, that is title, and person, the boss is a person that is a nested type. That's a schema. Again, should feel familiar. String and string, these are atomic types. Title, person, these are complex types and so on. Okay, so you see, now that we have been able to use data models, JSON schema, JSON, we can build data frames if the data is homogeneous enough. And if our data set can be validated against a schema, it can be more homogeneous and the querying will be more efficient because we can compress the way that we can store it, right? Now, about the real world. In the real world, if you download something from randomly found over the internet, it's more likely it's going to be on the left, some heterogeneous dump of JSON. If you want to feed that into a machine learning system, it won't work. You need to clean it up first. And a typical thing that you need to do before machine learning is data preparation. You need to clean everything to add the missing values and so on, simplify it, make sure it's homogeneous. Then you validate it against a schema, and then you store it as Parquet or some binary file. And then you can go ahead and query it or feed it into machine learning. That's kind of how the pipeline works, to give you the ground scheme of things. Okay, that's pretty much it for the data validation. Okay, who was following this? Okay, so now you can draw trees, you can draw data frames if you have a schema, and you know that you should consider using Parquet instead of JSON if you can convert your collection to a data frame. Okay, and I think we even have exercises for that will show you how you can use RumbleDB to create this Parquet file. Okay, so I'm stopping this one here, and then I'm moving over to MapReduce, which I will start today, and then we'll continue next week.